These are the answers to the AP Chemistry packet that covers topics 1.4 to 1.6. On this slide, you can see Unit 1 at a glance. Unit 1 is entitled Atomic Structure and Properties. In this video, we'll take a look at Topic 1.4, Composition of Mixtures, Topic 1.5, Atomic Structure and Electron Configuration, and Topic 1.6, Photoelectron Spectroscopy. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Topic 1.4, Composition of Mixtures. Here are some essential knowledge statements from the AP Chemistry course and exam description. Pure substances contain atoms, molecules, or formula units of a single type. Mixtures contain atoms, molecules, or formula units of two or more types whose relative proportions can vary. Elemental analysis can be used to determine the relative numbers of atoms in a substance and to determine its purity. All right, we'll start with question number 1. We are given a table that includes the mass of sodium chloride, the mass of magnesium chloride, which when added together give us the total mass of a mixture. Answer the following questions about the mixture whose composition is listed in the table above. Part A, calculate the percentage of sodium chloride by mass in this mixture. Read the question carefully. You do not need to use information from the periodic table to do this calculation. If you recall, in topic 1.3 from the previous video, where it was about composition of pure substances, we might have to consult the periodic table to figure out the total mass of sodium chloride, the molar mass, the formula mass. But here, the part divided by the whole involves the mass of sodium chloride and the mass of the entire mixture. So the calculation in this particular part of the question, the percent of sodium chloride by mass is 2.75 grams of sodium chloride divided by 6.17 grams for the entire mixture. So that's the percentage of sodium chloride by mass. Our calculation gives us 44.5705. That's way too many significant figures. Let's go ahead and round this off to 3 significant figures since each of the measurements has 3 significant figures. So we'll call this 44.6% sodium chloride in this particular mixture. Okay, let's take a look at part B. Calculate the percentage of sodium by mass in this mixture. So now we do need to consult the periodic table to get information because sodium chloride is a pure substance that contains sodium. So there are 2 components of this mixture, sodium chloride and magnesium chloride. Obviously, only one of them, sodium chloride, contains sodium. So our first step in this calculation is to figure out how many grams of sodium are present in the mixture. So on the periodic table, we can find the atomic mass of sodium, 22.99, atomic mass of chlorine, 35.45. Together, that's 58.44 for the formula mass or the molar mass of sodium chloride. And so if I have 2.75 grams of sodium chloride, how many grams of sodium are present? So we're going to set up a conversion factor that puts grams of sodium chloride on the bottom and grams of sodium on the top. We use the information from the periodic table to do this calculation. So multiply by 22.99, divide by 58.44, and this gives us, on our calculator, 1.0818 grams of sodium. I'm not going to round off that answer just yet because I'm not done, so I'll just carry that forward. The percentage of sodium by mass in the mixture would be the mass of sodium divided by the total mass of the mixture, which we know is 6.17. So grams of sodium over grams of mixture times 100, And now I'll round this off to 3 significant figures. So we'll call this 17.5% sodium by mass. Okay, moving on to part C of this question. Calculate the percentage of chlorine by mass in this mixture. So this one's a little more challenging because, as you can see, we have sodium chloride and magnesium chloride. So each of them contains chlorine, and so we have to figure out how much chlorine is there in sodium chloride, how much chlorine is in the magnesium chloride, and then add those two masses together. So let's take a look at the information from the periodic table for magnesium chloride. Magnesium has an atomic mass of 24.30, chlorine 35.45, and there are 2 of them. So the grand total, 95.20. That's the formula mass or the molar mass of magnesium chloride. So we'll do it one step at a time. Sodium chloride, 2.75 grams. Let's calculate how much chlorine is present in 2.75 grams of sodium chloride. Grams of chlorine on the top, grams of sodium chloride on the bottom. Again, that comes from the information, the periodic table. We'll do that math. So times 35.45 divided by 58.44, 1.668 grams of chlorine. And just kind of put that on the side for a moment, and we'll repeat the process for magnesium chloride. 3.42 grams of magnesium chloride. Let's figure out how much chlorine is present in that sample. Remember that there are 2 chlorines in the formula. So the mass of chlorine is not 35.45, but rather 70.90, divided by the total mass of magnesium chloride. Again, that comes from the information in the periodic table. So times 70.90 divided by 95.20, and that gives us 2.547 grams of chlorine. So those 2 quantities of chlorine are now added together to give us 4.215 grams. That's the total mass of chlorine in this particular mixture. So one more step, grams of chlorine divided by the grams of the mixture. 4.215 divided by 6.17 times 100. We'll round our answer off to 3 significant figures based on the number of sig figs in each measurement. So we get 68.3% chlorine by mass in this mixture. Okay, let's take a look at number 2. A sample of solid labeled as AgNO3, which is called silver nitrate, may be impure. A student analyzes the sample and determines that it contains 68% silver by mass. So earlier in this video, I had talked about one of the essential knowledge statements for topic 1.4, which is that elemental analysis can be used to determine the purity of a sample. So we don't know for sure if this sample of AgNO3 is pure or contains some other component, some other substance that would make it a mixture. So part A, calculate the percentage of Ag, of silver, by mass in a pure sample of AgNO3. So the skill that you need in this particular part of the question is what we already talked about in topic 1.3, elemental composition of pure substances. Let's consult the periodic table. Let's get the atomic mass of silver, nitrogen, and oxygen. So we have 107.87 for silver, 14.01 for nitrogen, 16.00 for oxygen, times 3. So total mass, 169.88, the molar mass or the formula mass of silver nitrate. So the percentage of silver by mass in a pure sample would be the mass of silver, 107.87, divided by the total mass of the compound, 169.88 times 100, and we get 63.498, which when rounded off to 3 significant figures, and again, I'm just picking 3 significant figures kind of at random. We don't actually have any more details as far as measurements from the laboratory, but I'll go ahead and just call this 3 significant figures, 63.5% silver by mass. All right, before you move on to part B, let's kind of just take a moment and process. Now that we know the percentage of silver in a pure sample of silver nitrate, we go back and look at what it said in the question that the solid that was analyzed by the student was 68% silver by mass, not 63.5. So we already know that this sample of silver nitrate is not pure, that it contains some other substance. So we're talking about a mixture. Okay, this is part B. Which of the following is more likely to represent the solid sample that was analyzed by the student? Justify your answer. So now that we know that this is not pure AgNO3, but rather a mixture, is it more likely to be a mixture of silver nitrate and silver chloride, AgCl, or is it more likely to be a mixture of silver nitrate and silver bromide, AgBr? So remember that from part A, pure silver nitrate is 63.5% silver by mass. This particular mixture of silver nitrate and some other substance is 68% silver by mass. So we're thinking which substance, silver chloride or silver bromide, would cause the percentage of silver by mass in the mixture to be higher, to be greater than 63.5%. So how do we do this? Well, we have to look at the information from the periodic table for silver chloride and for silver bromide and run those numbers. So the molar mass of silver chloride is just the sum of the atomic masses of silver and chlorine. That's 143.32. The percentage of silver by mass in silver chloride is the part divided by the whole. So 107.87 for silver divided by 143.32 for silver chloride times 100. 75.3% silver by mass. Let's move on to silver bromide and do the same kind of calculation. So AgBr, 107.87 for silver, 79.90 for bromine. Again, the part divided by the whole. So mass of silver divided by the total mass of silver bromide. And we get 57.4%. Remember, we're looking for which of these mixtures would be more likely to represent the sample that was analyzed by the student. Since the percentage of silver in this particular mixture is greater than what it would be for pure silver nitrate from part A, it's greater than 63.5%, then we're looking for what would cause the percentage to be too high, not too low, but too high. And since 75.3% is higher, then that represents an impurity. The impurity would cause the percentage overall in the mixture to be too high. So hopefully that justification makes sense. All right, let's take a look at question 3. A student needs to analyze a mixture that contains barium chloride, BaCl2, and sodium chloride, NaCl. The student dissolves a 6.75 gram sample of this mixture completely into water and adds an excess amount of sodium sulfate aqueous. Again, sodium sulfate Na2SO4. A white precipitate of barium sulfate, BaSO4, solid, is formed based on the following chemical equation. The solid precipitate is filtered, dried, and weighed, and its mass is recorded as 2.36 grams. So part A, calculate the number of moles of barium sulfate, BaSO4, that is recovered in this experiment. So to do part A, we don't need to worry about the balanced chemical equation. All we're doing is converting grams into moles. So we'll consult the periodic table. Barium sulfate is barium, so 1 barium, 1 sulfur, and 4 oxygens. 137.33, 32.06, and then 4 times the atomic mass of oxygen. Grand total, 233.39 grams per mole. Let's take our grams of barium sulfate, 2.36 grams. We'll set up a simple conversion factor based on the molar mass. So times 1 mole over 233.39. We'll round off our final answer to 3 significant figures. So we get 0.01011, which when rounded to 3 significant figures based on the measurement 2.36 grams, 0.0101. Again, that's the number of moles of barium sulfate. Now, we haven't talked about the mixture yet, But as we move from part A to part B, we'll see how we can connect the mass of the precipitate, the barium sulfate, to the mass of one of the components of the mixture. So here's part B. Calculate the percentage of barium chloride by mass in this mixture. So now we are going to need to make a reference to this balanced chemical equation so we can connect the product to the reactant. So in terms of the strategy for solving part B, first we're going to have to take moles of barium sulfate, which we got from part A, and convert that into moles of barium chloride. Then we're going to have to go to grams, convert moles into grams for barium chloride. And then since we know the total mass of this mixture, we have to calculate the percentage of barium chloride by mass in this mixture. We're going to need the molar mass of barium chloride. So again, from the periodic table, barium and chlorine, there are the atomic masses, 1 barium and 2 chlorines. So for a grand total of 208.23 grams per mole, that molar mass of barium chloride is going to be used in this calculation. Let's start with our answer to part A. So 0.0101 moles of barium sulfate. That was the precipitate that was recovered in this experiment. How do we convert from moles of one chemical to moles of another? Well, normally we would use the coefficients, but we're in luck in that the coefficients are just 1 and 1. So in fact, that's a really simple conversion to go from moles of barium sulfate on the right to moles of barium chloride on the left. It's a 1-to-1 ratio. Then we use the molar mass from the periodic table. So 208.23 grams of barium chloride per mole. And we do this calculation, and we get 2.103 grams of barium chloride. So recall from the information in this problem that the mixture that was used in this experiment is 6.75 grams. And now that we know the mass of barium chloride that was present in this mixture, we can do that final calculation. So the mass of barium chloride, 2.103, divided by the total mass of the mixture, 6.75 times 100, gives us a final answer to part B. And we'll round this off to 3 significant figures. So again, based on the measurements that we have, 3 significant figures for the mass of the mixture, that limits our answer. So we'll call this 31.2% barium chloride by mass in this mixture. Okay, let's take a look at question 4. A mixture of calcium carbonate, CaCO3, and sodium carbonate, Na2CO3, is found to contain 35.00% sodium by mass. Calculate the percentage of sodium carbonate, Na2CO3, by mass in this mixture. Now, since all we have in terms of numbers is 35.00% sodium by mass, we don't know the mass of the mixture. Let's go ahead and make the assumption that the mass of the mixture is 100 grams, because percentages are based on 100. So if we assume that the total mass of the mixture is equal to 100 grams, then the mass of sodium present in the mixture would be 35.00 grams. We're going to need to consult the periodic table to figure out the formula mass or the molar mass of sodium carbonate. So the molar mass of sodium carbonate is based on 2 sodiums, 1 carbon, and 3 oxygens. So the grand total, the formula mass or the molar mass, is 105.99. Now, if we know that 35.00 is the grams of sodium, can we use the information from the periodic table to convert from grams of sodium to grams of sodium carbonate? Yes. So we'll start with 35.00 grams of sodium. Let's put grams of sodium on the bottom and grams of sodium carbonate on the top. This comes directly from the information on the periodic table. Notice that my grams of sodium is not 22.99, but rather 45.98, because that is the total mass of sodium within the formula Na2CO3. So again, pay attention to subscripts when you're considering how much of the sodium is present in 105.99 grams of sodium carbonate. So we do this math, multiply by 105.99, divide by 45.98, and we get 80.6796 grams. I'll go ahead and call that 80.68 grams of sodium carbonate. That would be present in 100 grams of the mixture. That was part of our initial assumptions. So the mixture contains 80.68 grams of sodium carbonate. So the percentage of sodium carbonate by mass, 80.68. Now let's take a look at our next topic. This is topic 1.5, atomic structure and electron configuration. Here are some essential knowledge statements from the AP Chemistry course and exam description. The atom is composed of negatively charged electrons and a positively charged nucleus that is made of protons and neutrons. Coulomb's law is used to calculate the force between two charged particles. Now on this slide you can see an equation listed. This is Coulomb's law. This equation is also listed on your AP Chemistry equations and constants sheet. But I will say that you don't need to do any mathematical calculations involving Coulomb's law on the AP Chemistry exam. What you need to know about Coulomb's law is more of a qualitative comparison. So with Coulomb's law, we have two charged particles. Now, if those charged particles have opposite charge, such as positive and negative, then this will be an attractive force. If these two charged particles are both positive or both negative, then this force will be a repulsive force. And what you can see in this equation is the following. The magnitude of the Coulombic force is directly proportional to Q1 and Q2, which represent the magnitude of the charges on those charged particles. The magnitude of the Coulombic force is inversely proportional to r squared, where r represents the distance between these two charged particles. And I will say more about Coulomb's law later in this video. The next essential knowledge statement says, in atoms and ions, the electrons can be thought of as being in shells, or energy levels, and subshells, or sublevels, as described by the ground state electron configuration. Inner electrons are called core electrons, and outer electrons are called valence electrons. The electron configuration is explained by quantum mechanics as delineated in the Aufbau principle and exemplified in the periodic table of the elements. The relative energy required to remove an electron from different subshells of an atom or ion, or from the same subshell in different atoms or ions, ionization energy, can be estimated through a qualitative application of Coulomb's law. This energy is related to the distance from the nucleus and the effective shield charge of the nucleus. Now, let's take a look at question 5 in your packet. The valence electrons of both sodium and magnesium are located in the third energy level. Which atom, sodium or magnesium, experiences a greater attractive force between the nucleus and the valence electrons? Justify your answer in terms of Coulomb's law. So again, when I say Coulomb's law, you should be thinking about both charge and distance. Let's go ahead and compare sodium and magnesium and see if the comparison has more to do with the charge or the distance. So I've drawn a model here of the sodium atom. You see sodium has 11 protons and 11 electrons. So there's a nucleus that has a positive charge of plus 11. And then we have the electrons in various shells, 11 electrons. Now we have magnesium, which has 12 protons and 12 electrons. And we're looking at a nucleus that has a charge of plus 12. And again, there's the electrons in different shells. So Coulomb's law has to do with charge and distance. So if you're not sure if this is more about the charge or the distance, let's take a look at the information in the question. The valence electrons of both sodium and magnesium are located in the third energy level. So in terms of distance, the electrons are approximately the same distance away from the nucleus if they're both in the same energy level. But what about the nucleus? Well, one of them has 11 protons, the other has 12 protons. So here we are comparing the attractive force between the valence electrons and the atomic nucleus. Since magnesium has more protons than sodium, there is a greater magnitude of charge on the nucleus. And the greater the magnitude of charge, the greater the attractive force between the nucleus and the electrons. So the correct answer to number 5 is that magnesium should have a greater attractive force between the nucleus and the valence electrons. So this question was about the magnitude of charge. It was not really about the distance. All right, so in question 5, the comparison between sodium and magnesium, that was more about the magnitude of charge on the nucleus. Here, in question 6, the comparison between sodium and potassium, it's going to be more about the distance between the nucleus and the valence electrons. Okay, so number 6, the valence electron of sodium is located in the 3rd energy level, whereas the valence electron of potassium is located in the 4th energy level. Which atom, sodium or potassium, experiences a greater attractive force between the nucleus and the valence electron? Justify your answer in terms of Coulomb's law. So here is our model of the sodium atom, 11 protons, 11 electrons. And then here is our model of the potassium atom with 19 protons and 19 electrons. You might be thinking that positive 19 is a greater magnitude than positive 11, and somehow that would be important. But it turns out that when you change to a higher energy level, that distance between the nucleus and the outer electron shell is going to be the more dominant thing in terms of Coulomb's law. This is about the distance. So Coulomb's law has charge and distance, but here we're going to focus on the distance. So the distance between the nucleus and the outer shell, that's what's going on here. We're comparing the attractive force between the valence electrons and the atomic nucleus. Sodium, the electron, the valence electron of sodium, is closer to the nucleus than the valence electron of potassium. So the smaller distance between the oppositely charged particles, the greater the attractive force between them. So the correct answer to number 6 is that sodium should have a greater attractive force between the nucleus and the valence electron. And again, this is not about the magnitude of charge, it's about the distance between the outer electron and the nucleus. Okay, let me do a quick summary of the information that was presented in questions 5 and 6. Here's sodium and magnesium. You'll notice that they are located in the same period, the same horizontal row of the periodic table. When comparing the atoms of 2 different elements that are located in the same period, the valence electrons of each atom are located in the same energy level. So in this case, it was energy level 3. The element with more protons has a greater nuclear charge. Again, that was magnesium. And there is a stronger attraction between the nucleus and the valence electrons. So in general, according to Coulomb's law, the greater the magnitude of charge, the stronger the attractive force between oppositely charged particles, such as the nucleus and the outer shell electrons. On the other hand, when comparing the atoms of 2 different elements that are located in the same group, the same vertical column, the valence electrons of each atom are located in different energy levels. So sodium's outer shell is level 3. Potassium's outer shell is level 4. So the electrons that are located in a higher energy level are farther away from the nucleus. Electrons located in a lower energy level are closer to the nucleus. So according to Coulomb's law, the smaller the distance between oppositely charged particles, the greater the attractive force between them. So the electrons that are closer to the nucleus will be more strongly attracted. Okay, let's take a look at question 7. Ionization energy is normally expressed in units of kilojoules per mole and is defined as the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms or ions in their ground states. This process is represented by the equation below. So the equation shows an atom of X, some element. And then on the right, we see an ion with X having a +1 charge as it lost an electron. So the ionization energy, the energy required to remove an electron from an atom or an ion. So based on your answers to questions 5 and 6, arrange the atoms sodium, magnesium, and potassium in order of increasing ionization energy value. So what that means is that on the left, the lowest ionization energy value that we put in this table would be the atom that requires the least amount of energy to remove the outer shell electron. And on the right of this table, the element that has the highest ionization energy would be the one that requires the most energy to remove the outer shell electron. So if you recall the answers to questions 5 and 6, sodium had a stronger attraction for its valence electron as compared to potassium, because the sodium's valence electron was an energy level 3 as compared to potassium's valence electron and energy level 4. So the sodium's valence electron was closer to the nucleus and more strongly attracted. And then when we compared sodium and magnesium, because magnesium had one more proton in its nucleus, that meant that the electron in that outer shell, level 3, was more strongly attracted to the nucleus because of its greater magnitude of charge. So potassium, the easiest to lose the outer shell electron; magnesium, the hardest to remove the outer shell electron. Okay, so now we're going to transition to discussing electron configuration. So before I do that, we'll take a brief view of some of the features of the Bohr model of the hydrogen atom. Electrons travel in orbits around the nucleus. Only orbits of certain radii corresponding to certain specific energy values are permitted for the electron. An electron absorbs energy when it moves farther away from the nucleus from a lower energy level to a higher energy level. An electron releases energy when it moves closer to the nucleus from a higher energy level to a lower energy level. The letter N refers to the principal quantum number, or the electronic energy level. The lowest energy level for a hydrogen atom, N equals 1, is called the ground state. The higher energy levels, N equals 2 or higher, are called excited states. And while the Bohr model of the hydrogen atom is important to study, it is a primitive, inaccurate model. And today, we do not think of electrons as moving in orbits around the nucleus. Instead, we use the term atomic orbital, which is a mathematical function used to describe or indicate the probability of finding an electron. We can visualize atomic orbitals as electron clouds, these three-dimensional regions in space where we have a certain probability of finding an electron. And in terms of the orbitals, they have both a number, 1, 2, 3, 4, etc., and also a letter, S, P, D, or F, and those have to do with the shape, the features of that three-dimensional orbital. So S and P and D and F refer to different shapes of these orbitals, these electron clouds. The electron configuration is the distribution of the electrons in an atom or an ion among the various orbitals. There are patterns on the periodic table that help you write the electron configuration of an atom or an ion. All right, let's go ahead and take a look at question number 8. We're given element symbol, atomic number, complete electron configuration, and the noble gas abbreviated electron configuration. So again, this should be a review of things you have already learned about electron configuration. Let's take a look at our first row of the table where we have oxygen, atomic number 8. The electron configuration is 1s2, 2s2, 2p4, and the abbreviated version of that would be helium in brackets, followed by 2s2, 2p4. Okay, so our job in question 8 is to fill in the missing information in this table. So we'll start with The noble gas abbreviated configuration for an element, this is neon, and then followed by 3s2, 3p1. So here's our periodic table. We know that there are patterns on the periodic table for determining the electron configuration of an element. So the first row or the first period of the periodic table would be hydrogen and helium, that's 1s2. Then the second period, lithium and beryllium, that would be 2s2. And then from boron all the way to neon, that particular region would be 2p. So all the way to the end would be 2p6. Sodium and magnesium in period 3, that portion would be 3s, so 3s2. And then this particular electron configuration stops at 3p1. So the element is aluminum, which has 13 electrons, full configuration 1s2, 2s2, 2p6, 3s2, and 3p1. All right, moving on to calcium. We know the symbol, we know the complete electron configuration. So the atomic number of calcium happens to be 20. And if we go beyond 3p6, we go to the fourth period, that would be 4s2. So there's calcium with its complete electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. We put argon, the noble gas argon, in brackets, and then followed by the outer shell, 4s2. All right, we have atomic number 26. So we go find that element, which happens to be iron, Fe. And this particular region of the periodic table, the transition metal, that would be 3D. And if we count over to iron, that would be 1, 2, 3, 4, 5, 6. So the last part of the electron configuration would be 3d6. So there's the complete electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. We put argon in brackets, followed by 4s2 and 3d6. And our last two elements in this table are arsenic, As, and cadmium, Cd. Let's go find arsenic on the periodic table. That would be atomic number 33. So after the 3d10, it would be 4p, 1, 2, 3. So there is arsenic's complete electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p3. We put argon in brackets, followed by the last portion of the electron configuration, 4s2, 3d10, 4p3. Then now we get to cadmium, which is atomic number 48. So going to the fifth period of the periodic table, that would be 5s2, and then 4d10. That's where cadmium is located. So there's the complete electron configuration, and then there's the abbreviated configuration, putting the noble gas krypton in brackets, followed by that last portion, 5s2, 4d10. Okay, so there are the answers to the missing information in the table for question 8. Okay, here is question 9. An orbital diagram is another way to represent the electron configuration. Each box represents an orbital. Each electron is represented by an arrow. Electrons that have opposite spins are represented by a pair of arrows pointing in opposite directions. Electrons are paired when they occupy the same orbital. An unpaired electron is an electron in an orbital without another electron of opposite spin. So in the first row of this table, which has already been done for us, we have 4 electrons because beryllium has 4 electrons, atomic number 4. So we have 2 paired electrons in the 1s orbital and 2 paired electrons in the 2s orbital. So now we come to the 2p sublevel. And so for nitrogen, that would be 7 electrons total. 1s2, 2s2, and then we have the last 3 electrons in separate boxes, separate 2p orbitals, and that's according to something called Hund's rule, which says that each of the orbitals on the same sublevel must have a single electron before they get a second electron. So this is the electron configuration of nitrogen. Right next door to nitrogen is oxygen, so that next electron would go into the 2p sublevel by pairing electrons in the same orbital. So 1s2, 2s2, 2p4. And then for sodium, we fill out the complete 2p sublevel, and the last electron would go into the 3s orbital. So again, another way of representing the electron configuration is called an orbital diagram. All right, this is question 10. The ground state electron configuration refers to the arrangement of the electrons in the lowest available energy levels. An excited state electron configuration refers to a situation in which at least one of the electrons has moved up to a higher energy level. So we have 6 possible electron configurations. Circle all of the following that represent an excited state electron configuration. So normally it goes 1s2, 2s2, 2p6, 3s2. Now, again, the first electron configuration that I see looks fine. It ends with 3p1. That looks normal. But in the second electron configuration on that top row, it says 1s2, 2s2, 2p5. So that's an excited state because one of the electrons has moved up from the 2p sublevel to the 3s sublevel. That's an excited state. Looking on the top row there, 1s2, 2s2, 2p6, 3s2, 3p6, that's normal. 4s1, that's the last electron configuration, or the last electron in the outer shell. On the second row here, we have 1s2, 2s1. Okay, so that electron in the 2s sublevel has moved up to the 2p sublevel. That's an excited state. And then our last example of an excited state would be this one, where an electron from the 3s sublevel has moved up to the 3p sublevel. Okay, so far we have talked about electron configurations of atoms. Now we're going to take a look at electron configurations of ions. In number 11, the first example is calcium 2+. So let's start with what calcium looks like as an atom. Calcium has a total of 20 electrons, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So that would be all 20 of calcium's electrons. There are 3 little bullets that I want to talk about, 3 little points here. And the first bullet point is when electrons are removed from an atom to form a cation, they are always removed first from the occupied orbitals having the largest principal quantum number or the energy level. So what's the highest energy level for calcium? It's going to be the 4s sublevel. So calcium 2+ has lost 2 electrons from the calcium atom. Therefore, the electron configuration would stop at 3p6. You might be thinking, why not just abbreviate this electron configuration as argon, the noble gas argon, Ar, in brackets? Well, the problem with that as an abbreviation is that you're not giving us the outer shell and not indicating the energy level and the sublevel. So even though argon is the noble gas that has exactly 18 electrons, you cannot just use that symbol as the only thing that you write. There always needs to be some indication of the energy level of the electrons, like where they're located. So if you abbreviate argon, in this case, 18 electrons, you have to write neon in brackets, which takes care of the first 10 electrons, followed by the outer shell, energy level 3, 3s2, 3p6. Okay, our next example of a ion is oxygen 2-. So here's what oxygen looks like with 8 electrons, 1s2, 2s2, 2p4. Now we're going to add 2 more electrons to this atom to make it an ion. When electrons are added to an atom to form an anion, they are added to the empty or the partially filled orbital that has the lowest value of n. So 1s is full, 2s is full, but 2p is partially filled. So those 2 electrons are going to go into the 2p sublevel, which brings it up to 1s2, 2s2, 2p6. Again, we cannot just simply write neon in brackets and nothing else. So to get that abbreviated version, I put helium in brackets, and I'm showing you the outer shell, which is the second energy level, 2s2, 2p6. Okay, our next two examples are iron, Fe, and we have a 2+ ion, and we have a 3+ ion. So how do we do this? Let's go ahead and start with what iron looks like. Iron has a total of 26 electrons. Here you can see the electron configuration, which goes all the way up to 3p6, followed by 4s2, 3d6. So I have to take away 2 electrons. Do these 2 electrons that I take away, do they come from the 3d sublevel, or do I take them from the 4s sublevel? This brings us to that third bullet point. Iron is an example of a transition metal. That's that middle region of the periodic table between group 3, so where scandium is located, which would be atomic number 21, and you can go all the way to atomic number 30, which is zinc, and that would be group 12. You can see that that region of the periodic table, those are the transition metals. So if a transition metal loses electrons to become a cation, the electrons are first removed from the valence s orbitals. In this case, that would be the 4s sublevel. Let's go ahead and take those away. And here is the electron configuration of the iron 2+ ion. So I wrote argon in brackets, which gets us up to 3p6, and then followed by that last portion of the electron configuration, in this case, 3d6. Well, what if I have to take another electron away? Where does it come from? As it says, if additional electrons are lost, then they are removed from the valence d orbitals. So my next electron is going to come from that 3d sublevel. And so I've already removed 2 electrons from the 4s level. I removed 1 electron from the 3d sublevel, and you can see that my electron configuration now stops at 3d5 instead of 3p6. So students will sometimes struggle with removing electrons from a transition metal atom. So this rule says to always take them from the s valence shell and then take them from the d valence shell. Now we're going to take a look at our next topic. This is topic 1.6, Photoelectron Spectroscopy. Here is an essential knowledge statement from the AP Chemistry course and exam description. The energies of the electrons in a given shell can be measured experimentally with photoelectron spectroscopy, or PES. The position of each peak in the PES spectrum is related to the energy required to remove an electron from the corresponding subshell, and the relative height of each peak is ideally proportional to the number of electrons in that subshell. So here's a little bit more background information about photoelectron spectroscopy before we take a look at question 12 in the packet. Photoelectron spectroscopy, or PES, is an experimental technique that involves the ionization of a sample by using a high energy source of light, usually ultraviolet or X-ray. The energy is absorbed by the sample, causing all of the electrons to be removed from the atom. And we can use PES to determine the following information: the binding energy for each subshell and the number of electrons in each subshell. The relative number of electrons is shown on the y-axis. The binding energy is shown on the x-axis. And the appearance of the x-axis for a typical photoelectron spectrum looks a little strange at first. It is sometimes presented as a logarithmic scale, and the highest binding energy values are located on the left, and the lowest binding energy values are located on the right. An example of a photoelectron spectrum, or PES, for a pure sample of an element is shown below. So this is question 12. We have a y-axis indicating the relative number of electrons, and on the x-axis, we have the binding energy, which goes from 0 on the right to a maximum of 20 on the left. And the units are megajoules per mole. Again, the energy required to remove the electrons is the binding energy. So number 12, on the PES diagram above, there are two peaks. Draw a circle around the peak that represents the electrons that are located closer to the atomic nucleus. Justify your answer in terms of Coulomb's law. So at first glance, you might think, well, how am I supposed to use the PES data to determine the location of the electrons to the nucleus? Well, think about Coulomb's law in terms of distance. Closer to the nucleus is a stronger attraction. Farther away from the nucleus is a weaker attraction. So we're going to circle this particular peak that has the higher binding energy. And that's because, according to Coulomb's law, the attraction between oppositely charged particles, in this case the electrons in the nucleus, that attractive force increases when they are closer together, as the distance between them decreases. So the higher the binding energy, the closer the electrons are toward the nucleus. Okay, let's take a moment to process what we have just learned from question 12. In a PES diagram, you have binding energy. The binding energy value represents the energy required to remove the electrons from a particular subshell. Coulomb's law tells us that the electrons that are located closer to the nucleus should have a stronger attractive force to the nucleus, so therefore the core electrons are closer to the nucleus and they should have a higher binding energy. In other words, require more energy to remove than the valence electrons, which are farther away in the outermost shell. So in this particular PES diagram, there's only two peaks representing the subshell 1s and 2s. So 1s electrons are closer to the nucleus, 2s electrons are farther away. And since the height of the peak tells us the relative number of electrons, this would be 1s2, 2s2. So we have a total of 4 electrons. That would correspond to the element beryllium, atomic number 4, 1s2, 2s2. Now we have just identified the element from the information in the PES diagram. So let's keep going on to question number 13 of your packet. We have a PES diagram for an unknown element. So we have to label each peak as either 1s or 2s or so forth with the subshell, and then identify the element that is represented by this PES diagram. Remember, the highest binding energy is going to be on the left. So that's going to be closest to the nucleus. And then after 1s would be 2s. The next highest energy level in terms of the subshell in level 2 would be 2p, and then followed by 3s. So with these 4 peaks, they have been identified from highest binding energy to lowest binding energy. The height of the peak would correspond to 1s2 in the case of the first example, 2s2. But notice that that third peak goes all the way to the top. It's going to be 3 times higher than the peak for 2s. So it's going to be 1s2, 2s2, 2p6. That last peak only goes up half as much as the peak for 2s. So it's not going to be 3s2. It doesn't go all the way. It's going to be 3s1. So that's why the binding energies are actually written in the reverse order from highest to lowest, because now you can literally read the electron configuration of the unknown element by reading it directly from left to right across the chart. So 1s2, 2s2, 2p6, 3s1, that's what we're looking at. So what element is this? Well, 3s1, that would be located in the third period in the first column, first group. That's going to be sodium. So the identity of the element is sodium. Okay, this is question number 14. So we're not looking at a PES diagram, but we are looking at some data for binding energy. The table above shows the binding energy for the 1s electrons in a nitrogen atom, and the binding energy for the 1s electrons in an oxygen atom. Explain the difference in these two values in terms of Coulomb's law and atomic structure. So remember that with Coulomb's law, it's going to be about charge or distance, depending on what we're comparing. So here we're comparing the 1s electrons of nitrogen with the 1s electrons of oxygen. So remember that these two elements are in the same period. It's a comparison of the atoms of two different elements in the same period. And since the 1s electrons of each atom are in the same energy level, this is not about the distance. It's about the magnitude of the charge. So what's the difference between nitrogen and oxygen in terms of charge? Well, in the nucleus, nitrogen has 7 protons, whereas in the nucleus of oxygen, there are 8 protons. The element with more protons has a greater nuclear charge and should experience a stronger attraction for these 1s electrons. That's why the binding energy for the 1s electrons in oxygen is greater than the binding energy of the 1s electrons for nitrogen. So the stronger the attractive force comes from the greater magnitude of charge, again, the charge of the nucleus. Okay, this is question 15. We're given a PES diagram that is incomplete. It says a partial photoelectron spectrum of pure phosphorus is shown above. On the spectrum above, draw the missing peak that corresponds to the electrons in the 3p sublevel. So what are we looking at from left to right? Well, the highest binding energy is on the left. Those are the electrons closest to the nucleus. That would be 1s. And then from left to right, that would be 2s, 2p, and 3s. But that's where it stops. Now, the 3p sublevel is not shown, but it should be somewhere further to the right of that 3s peak. Let's take a look at phosphorus on the periodic table. Phosphorus has a total of 15 electrons. 1s2, 2s2, 2p6, 3s2. So that's been shown to us in this PES diagram. The last part of it would be 3p3. So we have to show a peak on the diagram that is to the right, as in having a lower binding energy, and the height of the peak should show that it's got 3 electrons in the 3p sublevel. So I'm going to draw the peak that is to the right, and it goes up to the third little notch on that scale on the y-axis. So the peak that corresponds to the electrons in the 3p sublevel is shown in red on the diagram. The electron configuration of phosphorus, 1s2, 2s2, 2p6, 3s2, and then 3p3. So the peak is drawn on the diagram that has a height that corresponds to a total of 3 electrons in that sublevel. And again, it should be somewhere to the right of the 3s peak. Okay, question 16, the last question in the packet here. We're taking a look at 3 different photoelectron spectrum diagrams. And all we have to do is identify the element. So let's take a look at how we read the information in a PES diagram to get the electron configuration and therefore the identity of the element. So I'm going to go ahead and label from left to right 1s, 2s, and 2p. So therefore I have 1s2, 2s2, but then it's going to be 2p. It's not all the way to the top. It's going to be twice as much as the 2s, so it's going to be 2p4. So 1s2, 2s2, 2p4 allows me to identify the element. So 1s2, 2s2, 2p4 would be right there on the periodic table, and that is oxygen. All right, our next diagram, again, starting from left to right, 1s, 2s, 2p, 3s, 3p. Again, in order from highest to lowest binding energy. So 1s2, 2s2, 2p6, 3s2, and then that last one only goes up half as much as the 3s, so 3p1. What element is this that would end with 3p1? It's going to be right here So 3p1 would be aluminum. 1s2, 2s2, 2p6, 3s2, 3p1, that is aluminum. In our next diagram, again, we'll start from left to right. 1s, 2s, 2p, 3s, and 3p. This one, the 3p peak does not go all the way to the top. It's going to be just 5 and not 6. So 1s2, 2s2, 2p6, 3s2, and then 3p5. That's where it stops on the y-axis. So what element is this that ends with 3p5? It's right there, and that would be chlorine. So the identity of the element is chlorine. Okay, well, this brings us to the end of the video. Hopefully that these answers and explanations were helpful. Thanks for watching.